So welcome to the Picture Language Seminar again. I think this is our last seminar of the term, and we're really happy to have Zhengwei Liu again from Zhengwei University, and he's going to tell us about a new way to do quantum error correction. So Zhengwei, we look forward to your talk.
Thank you, Arthur. And this time I will talk about Alterfold theory and quantum error corrections. And different from the last talk I gave you in the past week. Now I will first talk about quantum error corrections. And then only at the end, I will mention how to update this idea using Alterfold theory. So now this is somehow more easier to access at the beginning. Let's go. Okay. Now, for the first part, this will be about our recent work on quantum error corrections. Essentially, we will talk about some graphical design of quantum error correcting codes. And the graph has parameters. So usually, graph doesn't have parameter, but here we're considering these parameters so that we can train those parameters for the variational graphical quantum error correcting codes and get better ones. And the general idea is that, well, for quantum error corrections, we may have some good codes that we already know in the literature. But in the experimental setup, the real noisy system may differ from the perfect noisy condition or noisy model we considered in the theoretical work. Then there are rooms to improve the code. Now we want to start with the known code and then train that better based on the real noisy model in the lab and to get better codes. So we want to test this idea, whether this will work. And this is joint work with the students Yuguo Zhao, Fuchuan Wei at Tsinghua, and Yongchang Li at Nanjing University, and Hao Zhan, Ben Wang. They are both at Nanjing University, and Zhaohui Wei and myself at Tsinghua University, and Li Jian Zhang is at Nanjing University. This joint work of different people from different places. And somehow the Tsinghua group are working on the theoretical part, and the Nanjing University group work on the experimental part. So for this talk, first I will talk about the classical idea in quantum error corrections and how do we understand using the first quon language rather than the general Alterfold theory. And then we update that by the end. And then we design quantum error correcting codes using the quon language. And this will involve the like graphs with continuous parameters and some heuristic constructions. And in particular, we will demo this idea using a 3-qubit quantum error correcting codes based on the amplitude damping noise. And then we will go to the 5-qubit quantum error correcting codes and illustrate some general idea. And we will show how this works very well by some concrete models and how to train those error correcting codes, and we compare the error rate for the physical qubits and other methods like previous designed error correcting codes and these new codes, and also explain how do we do this kind of numerical simulations. So this is essentially a hybrid training for quantum classical methods to design variational graphical quantum error correcting codes. For quantum error correction, essentially we have 3 key parts. One is the encoding map. We encode logical information by physical qubits. And then we have some noisy channel. The error happened. And then we want to build some recovery map. So we can get back to from the physical qubits to logical qubits. And we want to keep the information as accurate as possible. That means the composition channel should be closer to the identity map on logical qubits. And the difference of those composition channel and the identity map is the average fidelity. So we will count the quality of this recovery using this average fidelity. We have known that for the error correction, there are some very good quantum error correcting codes, like Peter Shaw's error corrections for repetition code, like correcting a single qubit error, like Pauli X. Just similar to the classical repetition code, it has a quantum version, and that's a 312 code. And then to correct arbitrary single qubit code, he generalized the idea. Just repeat that twice in the X basis and Z basis. Then that will correct arbitrary single qubit arrow. So that's a 9 physical qubit, 913 code. And later this is improved to the optimal code, the 513 code. We can correct a single qubit arrow using 5 qubits. And then there are some other very interesting code like the toric code, surface code, which contains the topological insights to do quantum error corrections. And essentially the logical information are determined by the underlying surface in the code design. And there are other kind of training idea to design quantum error correcting codes. Like previously there's a 4-qubit amplitude damping code that has a different noisy model and some like machine learning training parameters to design the code. And later we will compare our method and those previous methods. And one major difference is that those codes are designed somehow using no knowledge. We just design the code from the very trivial starting point. But here we will utilize the known data, like the perfect 1-qubit code, 513 code, to design better codes. And the major idea is that just in the realistic devices, the noisy is different from the code we are considering here, like 513. Here is just a random single qubit arrow. But maybe for a real quantum system, it could be like the amplitude damping noise, or like depolarization noise, or just maybe the poly Z arrow happened more than poly X arrow, just other situations. So we want to consider those as major factors to improve the codes. So tailoring the quantum error codes to specific noise is our labor-intensive task. And that's the part we will present in this work. And this requires extensive manual analysis for each individual case. And certainly this is the part that we only present the idea, somehow theoretical ideas in the general framework. But somehow this computation, numerical computation is case by case and based on the computer algorithms. And one essential idea we are going to use is the quon language. This makes the code design more graphical. It involves more information. And also it gives us extra position to design the parameters. That's the major point. Since in the usual tensor network, if you have a phase transformation, then this is essentially a label on the single line for the phase transformation, single qubit gate. But in the quon language, we have 4 lines to represent a single qubit. And then the phase transformation, like on the X basis, it will be a crossing on 2 lines. On Z basis, crossing on another 2 lines. So this gives us extra positions to design the code mathematically.
Can you do these codes for qubits?
We can do the code for qubit, but I think at current status, most people are just interested in the qubit case. And there is a crucial difference between qubits and qubits. For the qubit case, for most cases, we have efficient algorithms to estimate the cost function, which is not true for qubit case. So just for 2 different kinds of reasons. One, most of the experimental setting about qubits, and most people are interested in qubit case. And secondly, for the estimates of the cost function, there is a major difference. For qubit case, it could be polynomial, and for qubit case, it could be exponential. And why that happened? Because it will see there are radial diagrams showing up in the framework. And in general, it's just exponentially difficult to evaluate a not invariant. But for the qubit case, we have a special trick to solve this problem. And then we want to show how to present error correcting codes graphically and how to train the cost function to get better code. And here the cost function is just the average fidelity. And for different situations, somehow we can choose different cost function. But this is the one that represents the idea better for general noise, for general situation. Now, how do we look at the quon language? So here is a circuit. It's not written in the standard format, but if you are familiar with the quantum teleportation, it's that circuit. You have an input qubit here, and this is a Bell state, or the result shared by 2 parties. And then you apply a CNOT gate, and then measurement-based transformation. And this is a Hadamard gate. and measurement-based transformation. And finally, you get a quantum teleportation. Now, in the quon language, we have a dictionary to translate those gates or somehow black box in tensor network and get a refined structure. Each single line is written as a rectangular solid. And with the lines, the decoration line on the boundary surface. And somehow so far the line are parallel to rectangular. In general theory, it's not necessarily the case. And this is kind of a measurement that we glue the boundary by parallel of lines and different choice of pairs responding to different choice of bases, like poly XYZ bases. And the number k equals to 0 or 1, responding to the results of the measurement. And the left side is the sum of charge of pairs responding to the recovery map. And the pair of charge is a poly matrix. 0 is identity, and 1 is a poly X. And for other position, that could poly X, Y, or Z. That's a Kitaev map for on false strings. So this is essentially the quon language representation of the teleportation protocol. And somehow, when we introduce quon language, it's essentially just the manifold, string manifold, the bulk solid. It's a neighborhood of tensor network. And in the quon language, we can open the black box in the tensor network and present it by those lines. And those lines later, we will use those lines to design error correcting codes. Now here's the basis to present a single qubit in the quon language. We have 4 boundary points. You can consider the 4 boundary points as just as the endpoint on the square, the 4 endpoints. And there are different ways to connect them, and they correspond to different price of the basis, 0 vectors. And if you have a pair of charge, that will be the vector 1 in the corresponding basis. So in tensor network, we will have this abstract node with 1 leg for a single qubit vector. Now this is a refined expression in the quon language. And for single qubit gates, we will have like 1 input and 1 output. And here, 4 boundary points at the input and 4 boundary points at output. And we represent the gate using pair of Majorana Fermis. And here we present the pair as a pair of charge. And we put them on the same horizontal level. That means they're paired somehow by a dashed line. But for simplicity, we ignore this dashed line. And in general, if you have different pair of dashed line, they are differed by a phase. So if you want to have a single graph without superposition, then essentially you can ignore the global phase. So this is a simplified notation for a pair of charge. And there are additional computational tools, if you have 2 Majorana fermions on a single line, like C multiplies C, then they will cancel this identity map. And we will use that relation later. And this is the relation we mentioned that's essentially used, this one, essentially used for the qubit case, actually both. The charge can move under that without any factor, move above the line with a -1 factor. So somehow modulo this number, the charge can move freely. So this reduces the computational complexity. This one is really crucial. We can change the order of the bit by adding a pair of charge. And that's why we reduce the complexity of computing not immersed. And this doesn't hold for the QD case. That's why we essentially need this condition, just really crucial one. And the other crucial condition is the string genus. But since we have the surface, if the surface is round by a string, then we can remove them. So in this way, we can change the shape of the surface. And that's another crucial rule. And also when we change the shape of the surface, we want to get scalar. So this is not a linear sum. And that's also help us to get better or efficient classical computation of those tensor diagrams. So that's for the single qubit. Now for 2 qubit case, we just have 2 input disks, 2 output disks. And aside that, so here for the input and output disk, now we call that the time boundary disk. So at top is time 0 as input, and the bottom is time 1 as output. And aside, that's the space boundary. And we have those line decorations on the space boundary. It can be braided, it can have a charge of pairs, also a pair of charges. And somehow there are all those other presentations like braiding of charges. They are linear sums of strings. So essentially we have just the decorations of strings on the boundary surface, the space boundary. And this is a part that's different from the usual TKFT. In the usual TKFT, we have time boundary, but not space boundary. And here we have those additional space boundary. And indeed, we need the three manifold inside. So they are the boundary of the three manifold inside. And also we have additional decoration on the space boundary. And those are the useful data that we are going to use. And how do you imagine those abstract picture in the real physics system? You can think about this disk as a concentration. So, well, you can first think about this just as a physical qubits. And this will be a way to represent your circuit. You can also think about this as a logical qubits. In that sense, you will have a condensation of physical qubits in the disks. And they will take a Hamiltonian and ground state to represent this space. Just different way to think about these different models. So now for the repetition code, let's see how do we use those ideas. The usual repetition code has a logical qubits. For 0, that's the physical qubits will be 0, 0, 0, and for logic 1, that's 1, 1 for the physical qubits. And not then for this qubit, we can represent them using this quon graph. Like here we have 3 output disks, the small disk, no input. So essentially it's a 3 qubit state. That's the graph. And how do we read the value? Like how do we read this state, the coefficient? Essentially, you just look at you can feel this disk using the basis, namely you measure this qubit. So now if you fill this with a z basis, like 0 or 1, you will have a pair of, like you will have this type cup here. That means you fill that by 0. And that means we will measure this qubit to get the result 0. And then if you measure all 3 qubits, you may get 0, 0, 0. And what's the probability to get that? You just count the value after you fill the caps. You get 3 circles. And each circle has a value square root of 2. And then after normalization, you get this 0, 0, 0 as a possible outcome. Another possibility is 1, 1, 1. And you won't get 0, 1 in the measurement. If you have that, that means you will have a cup here, and this part will be cup with a single charge. Then you have a circle with a single charge, and that has value 0. So just by the quick computation, you will see the only possible outcome will be 0, 0, 0, and 1, 1, 1 with the same amplitudes. After normalization, we get this factor. That's how we present a state using the quon graphs. And what's the advantage to present a state in this way? We can see the stabilizers. And for this case, it has a, well, but we will see the stabilizer in the next page. Now for 1, 1, 1, you just add a pair of charts. That's an action, a poly X action here. Let's go to the next slide. How do we see the stabilizers for the states? So if you take like Z1, Z2, the poly Z, acting on this state, then it's the identity map. And Z1 means on this qubit 1, you have a pair of charge to present the poly Z. And on Z2, you have, let's say Z3, you have another pair of charge acting on this qubit. And then you can repair them. Like previously you have this pair and that pair. Now you can repair them. You have this pair and that pair. And then you cancel them. That's how you check the Z3, Z1 acting on this state is identity map. So that's the stabilizer of the state. And this checking has a graphical meaning, namely, if you have this, look at the orange line, if it's a cycle, then for the cycle, every time it passes, it goes into the qubit and then go outside. So nearby the cycle, it will be a poly word. Once you put a cycle, you have those poly action on the qubits. So then we represent this kind of poly word action by a cycle. And the cycle is always an identity map on the graph. Just because on each line, you have a pair of charge and they will cancel. So in this way, we represent the stabilizer, this algebraic concept, using the cycle, that's a geometric concept on the graph. So this is a major improvement. Now, if we look at the 513 code, they have those 4 stabilizers. And now if we present the ground state by this graph, we can actually check. Both we can use the measurement, read out all the amplitudes and see this is the same as 513 code. But the better way to check that is this is really the stabilized state under the stabilized group action. And for the same reason, how do we check this word? So for this code, if we put this cycle passing through the 4 qubits, 2, 3, 4, 5, like this cycle, this should be a stabilizer. And if you read out the corresponding poly word, you will have this x, z, z, x for the 4 qubits. And then you can rotate this by symmetry, you get the other stabilizers. That's how you get the stabilizer of the state. And actually, this is a general theory. So if you draw such a graph on the plane, and then you can count all the cycles, they generate a group. And this group will get the maximum size. If you have n qubits, this group will have size 2 to the n. And that's the stabilized group of the state. So all those states will be stabilized states. So that's one way to present those stabilized states. No,
for this, like, why is how can we read qubit 2 you have the x versus qubit 3 you have what's the
here is the orientation. This disk is parameterized by this orientation. So you have a starting point. And then you have the number 1, 2, 3, 4, 4 strings.
But I mean, you can start at any point, right? You can,
Yeah. Well, if you start with a different point, then that's a change of basis. So
you're saying you are regulating both the direction of this rotation and also the starting point?
So if you say if this is z basis, if you put an arrow here, then this becomes an x basis.
Oh.
So this gives a presentation of the stabilized state in the 513 code. Now we can further introduce the braiding as a linear sum of those like lines, and the braiding indeed satisfies the Yang-Baxter equation, and actually everything can move under the braiding. And also we can introduce a general parameter alpha just by taking this linear sum. And if we take the alpha with 2 parallel lines acting on as a single qubit case, so if the pair of charge represents poly x, then this will be the phase rotation in the x direction. If this represents poly z, then this is a phase rotation in the z direction. So this is general parameter. And in quon language, we know just if you have those charge diagram, weighted charge diagram without such crossing, then all the gates or tensor networks are Clifford. And if you have such kind of crossing on a plane, then this will be match gate. And if you combine them together, it's universal. So essentially, we have a universal presentation of somehow the usual generating site of somehow the universal generating site given by Clifford gates and single qubit gates. And this braiding also verifies the dynamic Yang-Baxter equation, and that's a way we can do somehow the estimates of certain quon language networks in an efficient way. So we have additional computational tools using such kind of braidings, using such crossings with the Yang-Baxter equation, and using the string genus relation that can change the shape of surface. And just I think 2 years ago, we realized this kind of string genus relation can go even further, and that corresponds to surgery theory of 3 manifolds. And that's how we extend the theory to Alterfold theory. So here, if you draw all the quon language as a neighborhood of tensor network, then essentially we always live in the 3D space. We want to go beyond 3D space, but the full theory will go beyond 3D space. And that somehow makes it even more interesting. Well, now here we will show how do we design a new code. Let's just take the toy model, but already interesting enough. We take 3 qubits. As we mentioned, this is the stabilized state in the repetition code. Now, how we start with that to get a more general code? We just add this phase transformation at the crossing. And you may wonder why do we add the crossing this way? And the answer is you just draw all possible diagrams to connecting those like 3 disks by strings, and somehow eventually it always reduces to this case. So just this is a simple improvement, but somehow the most important improvement. And then if we write down the qubit, this is for qubit 0, and this variation is additional phase transformation like this. That's the algebraic representation of this diagram. Now, similarly, you can write this for qubit 1, namely if you have a pair of charge, and here you have the corresponding pair of charge, and then you get this qubit 1. And you can check this is a oscillator basis. So that gives you one logical qubit space. But here, without knowing that, we can also check this is a oscillator basis on the graph directly, just using the quon language. Now we have a parameter, a single parameter that adapts the 3 qubit repetition code at a special position. Just for a special value alpha, you will get this, say, when alpha equal to 0, this is the original repetition code. Now we just look at the special parameter. What to make it more interesting? We consider this as a adapted 3 qubit repetition code, but now we use that to another noise rather than the poly X noise. Now let's take the amplitude damping noise. And the horizontal direction lambda is the strength of noise. And the vertical direction is the average fidelity for the error correcting channel. Well, here we also have method to design the recovery map to get something optimal. And then we can look at the green line is our variational quantum error correcting codes. So we can train the parameters just based on the different strengths of noise. We can train those parameters and get different codes, the green line. And the purple line is the previous methods of training such code called QVEC, given in this paper by Jonathan, Ramiro, Olsen, Cao, and Aspro Guzik. Because they also try to train the code for 3 qubits. And that's the purple line. So we get it slightly better than the purple one. And what's the red one? The red one is just the code without error correction. So the original physical noisy. And the blue one is the 3 qubit repetition code. So that means even though the repetition code is good for poly X error, but when we change the noise, you may get a worse code. Okay. But even though we start with a worse code, we can simply just train that a little bit. Then we get this better code. So it's kind of a minimal cost, but get a big improvement. And how many steps we need to train this cost function for the fidelity? If you look at this, for the purple line, the QVEC method, you can do this like 1, 2, 3, 4, 5 steps up to 10 steps. And then you get a benchmark, this purple line. Yeah. But for our case, you just train that somehow one time, you almost get a limit. Then for a second time, there's almost no room to improve that. This shows somehow the efficiency of this training program. Even for 3 qubit case, we can see this method, just very basic idea. We start with a code we know, even though maybe it's worse for this new error. We just take that and train the parameter, even a single parameter, and you just very simple step, maybe even one step, and we can get a pretty good code. So this, the kind of toy model, but very interesting model, already shows the efficiency of this method. Now, what's this parameter that we get? After training that, we get this parameter alpha is half pi. And then we can write down the logic qubit explicitly. This value here is just the square root of -1. And experimentally, we implemented this 3-qubit variational graphical quantum error correcting codes using photonic realization. Somehow they just using the photonic system to demo the noisy. And we checked just the full circuit and compute the fidelity experimentally. And the experimental work is given by this purple horizontal line, those dots. And our theoretical work is the green line. So somehow they match very well here. And another interesting thing is like the red line is no protection, and this orange line is the 3-qubit repetition code. One interesting thing here is we can compare our code, the green line. We can look at the threshold. At this intersection, that's where we have the threshold. So when the noise goes beyond 0.4, then the code will make it even worse. So that's the threshold for our code. Now we know the 513 code is pretty good. If we put that, we have this blue line. It's close to the green line at the beginning, and it goes down quickly, but noise gets bigger. And if we look at the threshold, it's here. Something like 0.27. So that means even we have a 3-qubit code, the threshold comes after the 5-qubit code.
So these new code words, are they still stabilized by the
This one? Yes. This is still stabilized code. That's just another stabilized code.
general, like your code guarantee that it's
No, later we'll see example. It's not necessarily stabilized code. Just in this case, we train a single parameter here, and when alpha is half pi, that means this is breeding. And if it's a breeding, there's no generic parameter, this will be a stabilized code. Yeah. Now let's look at the 5-qubit case. Well, even for 3-qubit case, we can get something better. So then we can just expect more for the 5-qubit case. And for 5-qubit case, it's more interesting because there are two classical code that's considered to be good. One is the repetition code to correct the poly X error, X and XX error. And the other is the 513 code to correct arbitrary single qubit error, like two different kinds of error model. So we can write down the stabilized state. For 513, we have mentioned is this graph, K5 connectivity graph. For the repetition code, it's the other graph. Actually, there are different ways to write it. And then how do we find the parameters to train the code? We give an interpolation of the two graphs. So what's the meaning of interpolation of graphs? So at the crossing, we put the parameter alpha. And since for different choice of the angle, this crossing may represent the breed, then we get the 513 code. It may also represent the identity map. Then we get the repetition code. So at different angle, get different code. Then a very basic idea. In this family, we already have repetition code and the 513 code involved. And then after training, you should expect it should be better. At least it won't be worse than the two code because you already have them in the database. So this guarantee the training program will give us something better. So then we want to train those parameters. Now to give you a better feeling, what's the meaning of those parameters? Now we rewrite that as a circuit. And this is a circuit for the original code. And now we can put those 2-qubit case for neighborhood interaction with those parameters. And those parameters really, like, for example, this parameter here nearby the first and second qubit. That really means a 2-qubit gates with the parameter alpha, and the 2-qubit gates is RZZ, the ZZ rotation. We have explicit meaning of this parameterized crossing in the circuit. And then this gives a family of codes with 5 parameters. Now we can take different kinds of errors. And then also for the error, since the repetition code and the 513 code corrects different type of errors. So we just set up the error with a parameter. Say when the parameter is 0, the error is designed for 513, the original one. So it's perfect. And when the parameter eta is 1, then the error is designed for repetition code. So in that case, it's perfect. But now we can have more general error between the two, the interpreted error. And actually, you can even input more other type of errors, and then you train this. Then you can see the green line is the final result, the outcome code. And the blue line is the 513 code. So on the left-hand point, with eta equal to 0, this green one is very close to the 513 code. And on the right side, when it's close to repetition code, because the green code is also close to repetition code. And if you don't do error correction, the red line is below that. It's just not good. And if you run this QEC, the previous method, it's this purple line. So this green line, our final result outperform all of them. And you can see in this case the power of the interpolation. Essentially, you would expect the function here that's bigger than the maximum of the blue one and the yellow one. Because when we do interpolation, they are already involved in family. So you won't get something worse. It has to be better than that. And then to get the recovery map, somehow we mentioned what's the encoding map is parameterized. And then we also need to train the recovery map. Here we use some idea in the match gate. As we put those diagrams with possible crossings and with parameters. The recovery map can be chosen as some other possible case, but somehow in this case, it's pretty efficient. And the general idea is this one. We have the original encoding map. Wait. Here we have some encoding map here, and we want to have some recovery map. And here, what's the meaning of just putting those crossings? That means in the quon language, in this mapping cylinder, there are some lines moving around the surfaces for the recovery, and you may have intersections that give you the crossing parameter. And you train your recovery map using the parameters. And this is training process for 3-qubit case. And that's already well, but anyway, since 3-qubit is very small, so this is an efficient way to get it. And for 5-qubit case, we just get something better by adding ancillary qubits. So this is the original encoding map. This is the recovery map for say 513 code. And here, since we have interpolation, we should not expect that this is the recovery map for everything. So we put some ancillary recovery unitary, something pretty random, and with ancillary qubits and the measurements. And then we train those parameters after the noise hacking as a recovery map. And from that, we can find some good recovery map. And actually, the recovery map is pretty close to the optimal one. And this is a general circuit. You have an encoding map and some noise that happened, and you have a recovery map. And when we compute the average fidelity, we can use the 2 design. We put a random unitary on both sides using 2 design. And we compute that. That's our cost function. And then we test this on a very explicit case. That's the IBM 5-qubit quantum system. And this is a real noisy parameter in their system. So from that, you can see the first qubit is the best. And the last one is the worst. Now we can check the quality of the error correcting code on this real quantum machine. So this is a 5-qubit machine, and we just use the idea that we can take a 513 code and train that use those parameters. And the final outcome is this blue line. And the green one is the numerical optimized code. Since you can use the convex optimization, as Shao mentioned, and then just training the encoding map and the decoder just alternatively. And finally, you'll get an optimal code. But that training process is pretty long. And actually, we just did that for the 5-qubit case. It take a really long time to get it. But then we compare that optimal code, numerical one, and with our code that can be trained in a very much shorter time. They're pretty close. So this shows the efficiency of this training process. And for no error correction, it's the red line. And this Q0 is the best single qubit among the 5. So we beat the best one. And if you take the 513 code in this case, you see this doesn't work very well, even though this is considered or even called the perfect code for single qubit error. But when we really write on the machine, it doesn't work that very well. So this idea gives a successful adoptions of the original code, even though it doesn't work well experimentally. Just by training that, we can get better codes even for uneven qualities of qubits. But that's the real situation. Now, just using this quon language, we can design those quantum error correcting codes by rewrite the stabilized code as graph and then interpolate different stabilized codes together using parameters. And then for those codes with continuous parameters, we can adapt them to specific noisy channels. And I think that's the most interesting part. So it's not just a general theory for some perfect noise, but some general theory design for very real life noise in this case. And for 3-qubit case, we find the optimal code and we have a experimental realization using photons. And in general, we can write down those variational answers for those connected graph to design general codes. And this gives a hybrid design for quantum classical scheme to get quantum error corrections. Now, what do we know more about from the quon language to the Alterfold theory? So in quon language, when we represent the 2-qubit gate, the 3 manifold inside will be the neighborhood of handle body. But in the general Alterfold theory, it's kind of topological quantum field theory with both space boundary, a set, and time boundary on top and bottom, and with decorations on the surface. And for the quon case, it's just the line decorations on the boundary, space boundary surface. And here we can really go beyond the 3 manifold, which are handle body or neighborhood of tensor network. Like handle body is a neighborhood of 1 skeleton. But here we say we can take a neighborhood of 2 manifolds, 2 skeletons, like neighborhood of a sphere or neighborhood of a torus. That gave additional new concepts in the Alterfold theory. And actually, this becomes much more powerful. So this can go even beyond like 3 manifold, not inside the R3. And there are many other powers to illustrate ideas for quantum information, for TQFT topological orders, and many other things. But here for quantum information, let's see how this actual concept should work. As for toric code, it's defined on a torus. It has two logical qubits and many physical qubits, like n squared or 2n squared physical qubits. Now we can represent the toric code just using the Alterfold. And actually, I made a misinterpretation in the paper 6 years ago, in the 2019 paper, when I write down quantum error corrections for toric code using quon language. There, I take 2 holes surrounded by 2 input disks. I call it logical input. So somehow to me, I thought, okay, two logic qubits really means two holes. But for toric code, it's on torus. Now in Alterfold theory, we can do this on torus. This is a time boundary. It's a 3-manifold, which is torus across the interval 0 and 1. And the input is just a torus. And somehow you can put arbitrary declaration on the input. But since this is on torus, you can move them by isotopy and finally shrink them. And essentially, you only have possible data that's this direction. This label could be just empty, that's 0, logical 0, or it has a dashed line. And that's logic 1. Or in the other direction, it could be 0 or 1. So essentially 2 logical qubits. And on the physical side, this is T cross 1. You have the lattice of physical qubits. And the square, for when you look at the square lattice to implement the toric code, you need the stabilizer given by the plaquette operator and the vertex operator. And in this case, both plaquette and the vertex operator becomes the last false cycle of this plaquette. So for each last false cycle, you will see it will be an action of 4 polywords on the 4 nearby 4 qubits. And then depending on the position, the alternating position, it will be 4 poly X or 4 poly Z. That's the toric code. So this gives a presentation from the logical qubit space to the physical qubit space. So that's the encoding map of the toric code. If you use the usual quantum circuit to write down the encoding map, the complexity is log n. Just toric code doesn't have a simple representation using the usual quantum circuit. But here we have a Alterfold presentation of this encoding map. And then you can use similar idea. Now you can put the string together and make a crossing and add additional parameters. And you can design further codes. And you can also take, if you don't change the torus, there is always 2 logical qubits. You can take another 2 logical qubits. 2 logical qubits divided code on the other side. And then interpret that with toric code. Just similar idea as we mentioned before. Add parameters, interpolate different stabilizer codes, and then you get those variational quantum error correcting codes in this general way. And the general theory is that just all those local circles are stabilizers of this code. This is just true. Previously, 6 years ago, we proved this result for stabilizer states, but not for stabilizer code. Now here we can prove this for stabilizer code. And also separating the logical information and the physical information. So in this way, you can design those variational codes. And it's an intuitive presentation even for toric code. This is already intuitive. And this is not the usual way to present a circuit. But it's actually much better to present a circuit in this way. And this presentation gave a very, very efficient fidelity estimation. And what's the key point of that? If an error happened here, we want to compute how this error affects this code, like when we count average fidelity. This error does not spread when you go backwards along time. If you go along the circuit, the single error will affect the full circuit in the space-time region. But here, this direction is time. This lattice is space. The time is constant 1. So in that sense, this is a depth 1 circuit, not in the usual sense, but in this topological sense. So the error doesn't spread out. And what's the significance of that? That means when we count this average fidelity, if you use the circuit, the computational complexity is exponential. If you use this presentation and evaluate that in the Alterfold quon language, that's polynomial. And that means we can train this code not just for 3 or 5 qubits. We can even train that for 300 or 500 qubits by this new idea. And that's just impossible before. And also we have ways to do circuit simplification. Like when you look at this lattice, we know how to translate this back to the ordinary circuit so that it can be implemented in the lab. But actually, that's not the only way to implement that. We can also use ancillary qubits and use measurements to implement the same thing. Like for Tori-code, the depth is 4. Here you can do the same thing using a depth 4 circuit based on measurement. So those are the additional advantage that's really give quite new insights and new computational tools and new theorems using those new mathematical structures. Thank you.
Thank you, Zhengwei, for a very beautiful lecture. I'm sure there's a lot of discussion. Yes, Alex.
So when you were looking to train a code on something like you begin with the core code, you can extrapolate from that the logical operators on that.
Yes.
I'm curious, when you do the training, how do you distinguish between like ending up with same code? By isotopy, like some codes would have the same logical operations on them.
So it's not by topic, but we put the crossing with parameter. We choose different parameter, you get different graphs. So when the parameter is 0, you may get the gradient. When the parameter is 1, you may get the identity. And for different choice of parameter, you get different stability codes. So essentially, we train those parameters.
You're able to cycle through all of it.
Yes. And then the question will be, where do we put the parameters? And that comes from this idea we interpolate different good stability codes. So each stability code gives you a graph there. You just look at the similarity of the two graphs, and then the minor difference between them. And then you use some parameter to interpolate this minor difference.
So if I have two different sets of the alpha values, they represent the same thing up to permutations.
Yes.
Depending on what I begin with.
Yeah.
With this efficient without the estimation, do you need to run it on hardware?
No, that's a very good question. That's another major advantage. I think the experimental people will be excited. In quantum machine learning, there is a big problem that we need to train the parameters by sampling the outcome. And that has extremely high cost. And also adjusting the parameter in the experimental lab is also extremely difficult. In this way, we can do the training program fully by classical computer in polynomial time. So,
But I mean, like, what kind of voice model? Like, you have some like cross operators to define language qubit as a place.
yes, you can have cross operator on each qubit as a noise.
But then, like, doesn't that require a lot of resources to like this?
Yeah, that seems require a lot of computational resources. And then in previous method, the answer is yes. It requires exponential resource. But in this new method, the answer is polynomial. That's the major power.
And for the IBM experiment, like how quickly you have the encoding map or the decoding map, and then you have the one qubit to upgrade.
Yes, here we don't measure 1 qubit. We just count the average fidelity. Well, if we want to measure 1 qubit, we can also do that computation, not that different. But somehow just the most conceptual one is the average fidelity. That's symmetric with respect to all qubits.
Talking about the recovery map. Is the recovery map a completely positive map?
Yes.
Is it so also a trace on?
Yes.
What is the cost of finding the recovery map?
That's a good one. Training the encoding map is so far polynomial using new methods. training the recovery map might be exponential.
Does
Some,
does it depend a lot on the specific error of the device you're
yes. Yes. Since they are general theory, we don't really need to know the recovery map when we train the encoding map. So for that step, it's polynomial. But given a good encoding map, that's actually a better approach compared to the previous kind of alternative training. Since there you need to do this alternatively, and the cost is very high. Now we can just train the encoding map first. And after we get the encoding map, then we train the recovery map. Yeah, but still, we don't have theoretical guarantee to show the training of recovery map is polynomial. And we don't really know whether that's the case. But for concrete example, like previous one, we write down those recovery map and we train those parameters. And we do get the recovery map in a reasonable time. But since if you go this up to 100, then it depends on the noisy model, depends on the code we have. So it's hard to predict.
Would you say that heuristically it's polynomial time bound?
For the recovery map, I don't think so.
Have you done numerical simulations for a system of that size?
No, not numerical computation. Since there we need to improve our code. So it takes some time to run the code, and but we have a program, the step by step. How do we find a good graphical code, LDPC code, and then how to train the parameters, and then how to write down this encoding map in a reasonable way, and how to train recovery map with certain circuit. And but still, even though in that case, it may not make the experimental people happy, since the experimental setup is still different from this. But this is pretty close to the usual setup in quantum error correction. Just getting closer.
I'm curious, if you make modifications to the surface code you're looking at, are you able to, while looking at like the alpha values, extrapolate like what exactly would change in the issue?
Yes, we do. And now we are working on the recent paper. We can train those parameters and to see the impact of this parameter to the fidelity. The local noise, how this affect the global fidelity. And that can be done. In that sense, just there are many tricks to train the parameters. You can train that one by one, you can train that all together. That there are many different tricks. But that's more kind of engineering problem. We cannot give a theoretical framework to show which one really works better. But somehow, just that's what happened in the experimental setting. We have to involve a lot of engineering problem, just so asymmetric in the system.
Are there any questions online? Well, if there are no more questions, I'd like to thank Zhengwei again for an absolutely beautiful talk, and we look forward to hearing more about it in the future.
Thank you.
Thank you.